Welcome to The Explainer. You know, it's so easy to picture the internet as just this invisible, weightless cloud floating effortlessly above us. But the truth? Our wireless world is deeply physically grounded in the dark, crushing depths of the ocean. Today, we are dissecting a high-stakes digital disaster. Really, it's a masterclass in structural vulnerability. We are investigating exactly what happens when the very planet we live on decides to break the internet. Let's rewind a bit and look at the timeline of January 15, 2022, the day an entire island nation was violently knocked off the global grid. At 0 hours, the Hunga Tonga Hunga Haʻapai submarine volcano erupted with this devastating, earth-shattering force. Just minutes later, an atmospheric pressure wave literally circled the globe at supersonic speeds. Hours after that, tsunamis pounded the islands of Tonga and rippled outward across the wider Pacific. But down beneath the dark, churning water, a totally different disaster was unfolding. Tonga's main digital lifeline to the outside world, a crucial submarine cable, was severed, and it would take a staggering 5 weeks of total isolation before that connection could be restored.
What's absolutely mind-blowing here is the sheer scale of the deep-sea destruction. This wasn't just a snapped wire. It wasn't a clean cut that engineers could just quickly patch up. We're talking about the total obliteration of massive sections of critical infrastructure. Repair crews eventually discovered that 92 kilometers of fiber optic lifeline had been destroyed. That is nearly 60 miles of highly engineered cable that was completely displaced, buried, or just shredded to pieces by the violent tectonic movement of the Earth.
Part 1. The Hidden Ocean Network.
To truly grasp what happened, we have to strip away the whole illusion of the cloud. The internet isn't in space. It rests down in the dark volcanic sediment of the ocean floor. Vast amounts of global traffic. Financial transactions, sensitive government communications, every text, every streaming video. It all moves through thin strands of glass that are barely the width of a garden hose. These fibers carry information as rapid pulses of light right on the seabed. Now, the entire system relies heavily on geographic redundancy, meaning if one route fails, data is just seamlessly redirected to another. But for islands and developing nations that rely on a single deep-sea route, well, a single point of failure means the lights go completely out.
Get this, surprisingly, the vast majority of submarine cable breaks, a massive 80%, aren't actually caused by dramatic geological events. They're just the result of everyday human maritime activity. We're talking about heavy commercial fishing trawlers dragging nets that crush a line, or maybe massive cargo ships inadvertently dragging their multi-ton anchors across busy shipping routes. Against that backdrop of daily human error, natural disasters, things like earthquakes, underwater landslides, and volcanoes account for only about 20% of all submarine cable faults globally.
So, the contrast between these two threats is incredibly stark. Human threats, they happen all the time, but they're highly localized. An anchor snags a cable, the network redirects the traffic in milliseconds, and honestly, you probably never even notice your video buffering. But geological threats, they might be rare, but they possess the terrifying power to violently transform hundreds of square kilometers of the seabed in an instant. They don't just snag one cable, they can wipe out all primary and backup routes simultaneously. It completely defeats the deep-sea redundancy the global system was designed around in the first place.
Part 2. How volcanoes break cables.
Now, I know it is incredibly tempting to picture some exaggerated Hollywood scene, right? Glowing rivers of magma directly melting a fiber optic cable. But the physical reality is actually far more massive, tactile, and frankly, terrifying. The true threat doesn't come from heat. It comes from kinetic force. When a submarine volcano erupts, it triggers catastrophic seafloor collapse and gargantuan avalanches of sediment that violently reshape the ocean floor.
And that brings us to a terrifying physical phenomenon known as turbidity currents. These are dense, violently turbulent underwater avalanches of rock, ash, and seawater. They often travel at highway speeds, sometimes well over 100 kilometers per hour, ripping across the ocean floor. When part of a volcanic structure collapses, it triggers these unstoppable flows. They can travel vast distances, following deep-sea valleys and destroying absolutely everything in their path. A cable doesn't even need to be anywhere near the volcanic crater to get wiped out. It just has to be in the path of this underwater avalanche.
The aftermath of this really shows the true scale of the violence. 30 meters. During the Tonga eruption, the domestic cable wasn't just cleanly cut. Underwater surveys later found that it was buried under 30 meters of dense, heavy sediment and volcanic ash. Just imagine the sheer kinetic force required to dump roughly a 10-story building's worth of rock and debris over a vast, pitch-black stretch of the ocean floor. That is literally what these cables are up against.
Part 3. The Deep Sea Repair Operation.
Fixing a break of this magnitude is definitely not an IT problem. It is a grueling marine engineering operation in a severely hazardous environment. Under normal circumstances, say a typical anchor strike, repairing a cable follows a meticulous, highly mechanical sequence. First, engineers fire light pulses from coastal stations to bounce off the fault and estimate its exact location. Second, a specialized cable ship sails out and blindly drags massive grappling hooks across the pitch-black seabed to catch the line. Third, they haul it on deck, meticulously cut away the damaged section, and splice in a fresh glass replacement. Finally, the repaired system is carefully lowered back down into the abyss. It's complex, sure, but it's routine.
But a volcanic disaster? It turns that routine repair into an absolute logistical nightmare. The cable isn't just broken once. It's snapped in multiple, totally unpredictable places, and then buried under impenetrable layers of rock and ash. And perhaps most terrifyingly for the marine engineers out there, the original bathymetric maps they rely on are completely useless now. The actual physical terrain of the seabed has literally been rewritten by the blast. Add in highly unstable underwater slopes risking further landslides, heavily damaged ports, a shortage of specialized ships, and it becomes painfully clear why it took 5 grueling weeks just to restore Tonga's connection.
Part 4. Global Chokepoints and Vulnerabilities.
Panning out from Tonga, this disaster serves as a stark warning for our entire global digital infrastructure. Think about what happens when a major data pathway is severed. Your data doesn't just disappear, it gets aggressively redirected. Under normal operations, capacity is high, latency is low, and you're getting seamless streaming across those direct ocean routes. But during a choke point failure, massive volumes of global traffic are suddenly forced onto narrow, low-capacity backup roads. Latency absolutely skyrockets, and users start experiencing dropped calls, severe congestion, and failing cloud services, even if the actual physical break is happening thousands of miles away in the Pacific. This fragile bottleneck exists because of what we call digital choke points. Submarine cables cannot just be dropped randomly anywhere. Engineers have to carefully navigate extremely deep water, busy shipping lanes, and complex seabed terrains. And that geographic reality forces many cables to converge in narrow straits or run straight through highly active tectonic zones. So the ultimate irony here is that while we think we've built this highly redundant global network, we have actually placed our primary and backup cables in the exact same corridors of physical risk.
Which naturally leads us to ask this critical question. Can we protect a network that rests on a moving planet? Seriously, how do we secure our internet when the very ground it rests upon is active, constantly shifting and occasionally trying to destroy it?
Well, network operators and marine geologists are definitely fighting back. Defense begins with exhaustive pre-installation seabed surveys, carefully routing around the most dangerous fault lines and steep slopes. Networks are also demanding true geographic diversity, making sure backup cables take completely different physical paths across the ocean. We are also seeing a lot of pre-positioning of emergency satellite terminals to act as immediate stopgaps. But arguably the most fascinating development is happening within the cables themselves. Researchers are investigating how to use the optical fibers as vast, deep ocean seismic sensors. By measuring microscopic changes in light pulses to detect pressure drops and seabed vibrations, they're effectively turning the internet itself into a global early warning system.
Because here is the stark reality. 2 cables running parallel to each other might look like perfect redundancy on a pristine office whiteboard. But down in the dark, sediment-covered trenches of the seafloor, they share the exact same fate. If a massive turbidity current sweeps through that underwater valley, both lines are wiped out instantly. Real redundancy requires incredible distance, vastly different geographic routing, and monumental financial investment.
I want to leave you with this final, provocative thought. We tend to treat our digital lives as if they exist purely in the ether. But the internet, even though it moves at the speed of light, still rests on the Earth, and the Earth does not sit still. The next time a page loads slowly on your screen, remember that your connection is traveling across a restless planet, one capable of violently severing our digital world without ever breaking the surface of the water. Thanks for joining me on this deep dive. Keep exploring, and I'll catch you on the next explainer.